So with that, I'm actually going to hand it over to Cody. I don't know if you saw, but Cody has sneakily joined our meeting, and he is an awesome graduate student at Stanford. And he is going to take over, and he's going to give us a sort of overview talk about what he does for research and sort of within the context of nanoscience and making nanoparticles. All right. So, Cody, are you able to share your screen?
Should be able to. You guys see it?
Okay, awesome. Yeah.
All right.
And then, yeah, I think for this, if you guys have any questions, I can monitor the chat box, and Jenny as well, and Karthika as well, and then we can sort of save the questions for Cody at the end. Sound good? All right.
Yep, that works for me. All right, thanks a lot, Angela, and thanks everybody for joining me. As Angela mentioned, my name is Cody Wrasman. I'm a fifth-year PhD student here at Stanford in chemical engineering, and I'm excited to talk to you guys a little bit today about making nanoparticles, which is what I've been doing for the past 5 years. But first, I'd like to tell you guys a little bit about myself. So I'm originally from Middleton, Wisconsin. It's a small town, maybe about 30 minutes outside of the state capital. Its biggest claim to fame is it is the home of the National Mustard Museum. So maybe you've heard of it through that, but probably not. While I was there, I grew up there my entire life. Going through high school, I had a lot of really great science teachers. And one thing that they really impressed upon me, or one thing I was really fascinated by, was the periodic table and chemistry in general, and how all of these rules kind of come together in chemistry to influence a lot of different aspects of our daily lives. So chemistry is responsible for making the fertilizers that we need to grow our food. Chemistry is needed for baking our food. It's needed for transforming oil into things that we use every day, like plastics and fuels. So really, every aspect of our life is touched by chemistry, and that's something that really interested me in high school. And I think more specifically, what I was really interested in was the application of chemistry on these really large scales, these processes that we rely on every day that use chemistry, and the transformation of chemistry from the lab scale to the industrial scale. And that's really what chemical engineers do. That's kind of the job of chemical engineers. So I decided that I would study chemical engineering as an undergrad. But even as I was going to start that, my mom, I think, saw something on the news and said she thought that I would be working with nanotechnology someday, even though I really had no inclination that was going to be happening when I was in high school. So with that, I moved from Middleton to the University of Minnesota in the Twin Cities. So here's a picture of campus when it looks really nice, and maybe a more indicative picture of campus while I was there. It was probably the coldest place that I've ever lived. But while I was there, I had a lot of great opportunities, both in classes and doing some formal research activities, both at the university, looking at some research into making solar cells with more earth-abundant materials, as well as industrial research and development, researching industrial drying processes. But both of those kind of came together and made me realize how much I enjoyed just the overall research process. And I had a lot of opportunities to talk to people in those research projects, and realized that if I wanted to get into this research space, moving on to a PhD was really the path for me. With that, I moved all the way out here to California. I've been working at Stanford for the past 5 years. Outside of the lab, I've had a lot of opportunities to kind of explore a lot of the different areas that California has to offer, backpacking and backcountry skiing, and all the mountains and the forests and the beaches. It's been great. But at Stanford, I joined a new professor in the chemical engineering department, Matteo Carniello. He had started maybe a few months before I had, and he asked me if maybe we could think about my project being developing a catalyst to convert methane into methanol. So being a new graduate student, I said that sounds great. I'm happy to have a project, and I went along with it. But what I didn't realize is that I was being talked into to kind of taking part of what is the thought of as the holy grail of catalysis, looking for that holy grail. So to take a little bit of a step back, all of this work's been done with all of the great coworkers I have in the Cornell group, and what we really try to do is leveraging nanomaterials for catalytic applications. And what catalysts do is they make chemical reactions easier. So if you think of trying to conduct a normal catalytic reaction, or a normal chemical reaction is kind of going over this mountain, catalyst can sometimes open up this tunnel to go through the mountain, makes the chemical reactions easier. And because it makes those chemical reactions easier, it makes the chemical reactions run much more quickly. And as a result, about 80% of all industrial chemical processes use at least one catalyst. And because of that, catalysts have a huge impact on overall global production of products. It's estimated that about 35% of the world's GDP is produced directly from catalytic processes. So these could be things like oil refining. There are many, many catalytic steps used in transforming oil into the fuels that we put into our cars, as well as into transforming oil into the plastic products that we use every day. There are many, many catalysts that are used to do that. Kind of the most famous catalyst in chemical engineering circles is the catalyst that's used to make ammonia. Ammonia is one of the biggest ingredients in fertilizers that we use to grow higher yields of crops. But people have looked into how many people are being fed directly from synthetic fertilizers that are being made from ammonia. And it's estimated that maybe around 3 to 4 billion people today wouldn't have enough to eat if they didn't eat food that was produced by synthetic fertilizers. So that ammonia process is very, very famous for that. And it's likely that many of us actually own catalysts that we use on a regular basis. The catalytic converters in our cars that are used to convert pollutants that are produced by the car's engines into more benign substances are examples of very common catalysts. But this is a talk about nanotechnology, so maybe you saw where this was going. The most common form of catalysts are metal nanoparticles immobilized on oxide supports. So this is a transmission electron microscopy image, so zoomed very, very far in, looking at one of these catalysts. So we can see these dark circles here are the metal nanoparticles, and this large kind of square rectangular areas are the oxide supports. So the reason that this type of shape is so common is something that I think you guys talked about recently is once you start going to these nanoscale particles, you can actually get enormous amounts of surface area from the same volume of material. And catalysis is something that relies on the surfaces of these metal nanoparticles, and therefore going to these nanoscale particles enables you to maximize the surface area for the amount of metal that you're using. And that's important since the metals that are used in most catalysts are actually some of the most expensive metals in the world. So things like platinum and palladium, the elements in your catalytic converter, are actually more valuable than gold. And as a result, it's very important to maximize the amount of surface area on these catalysts to make them affordable. And specifically, what I study is how different features of these nanoparticles impact catalysis. So there are a lot of different things that can be changed on a given nanoparticle, starting from this very basic nanoparticle catalyst design here. You can change the size of the nanoparticles. The shape of the nanoparticles can be changed. The composition of the nanoparticles, including multiple different metals, can be changed, as well as the support that the nanoparticles are put on can be changed. And that's kind of a lot of the different things that I think about on a day-to-day basis, how we can change all of these things to make these catalysts better. So I told you that we were looking into nanomaterials for catalytic applications. Specifically, what I'm looking into is how all these different nanoparticle features can be changed to dictate what products are made by chemical reactions when there are multiple different products possible. I mentioned to you previously that methane to methanol was kind of what I started out on. Methane is a very, very cheap and abundant gas. It'd be what's used to heat gas burner stoves, if you have any of those. It's frequently used in hot water heaters or furnaces to heat buildings. But really, energy is its most common application. If we compare that to methanol, methanol is a huge volume. Millions of tons of methanol, hundreds of millions of tons of methanol are produced a year. And it's most commonly used as a chemical intermediate to making a variety of different products like plastics. So maybe it's not obvious here what the big difference is, but the big benefit of transforming from methane to methanol is that methane is a gas and methanol is a liquid. And that's really important when you think that liquids are much easier to store and transport. And this comes into this becomes a big issue when you think about oil recovery or oil fields, where in addition to liquid petroleum that's coming out of the ground, a lot of methane is also being recovered at the same time. So in a lot of these places that are in relatively remote areas, like offshore oil platforms or oil fields in relatively remote areas, in a lot of cases, the methane that's recovered with the oil is just burned on site, simply because it's not profitable to recover the methane, and burning the methane is actually more environmentally friendly than simply releasing the methane into the air. But as you can imagine, that's actually a huge waste of this resource. So what I'm showing you here is a satellite image of the eastern half of the United States at night, and now zooming into a particular area. So some of the large cities have been labeled, particularly the Twin Cities right here. But from the large map and circled here, you see there's this very large blob of light that's showing up over the Dakotas, where there's actually no cities. And this large blob of light is actually being produced by this methane flaring. So there's so much methane that's being burned in these oil fields that it's visible from space. So it'd be great if we could start trying to recover that methane into a more valuable product that we could start using. I'm showing here the molecular structures of methane on the left and methanol on the right. You see that they're almost identical. You just have this extra oxygen inserted into methanol. So kind of naively, that seems like it should be a very easy transformation. We just need to oxidize one of these carbon-hydrogen bonds to form methanol. But the challenge really becomes, if you have conditions that you can oxidize one of those bonds, why wouldn't you just oxidize all of them? And that's actually what happens with all catalysts thus far. You oxidize all of those bonds, and you make carbon dioxide, which is not really a valuable product at all. So our hypothesis on this project was, maybe if we make the catalyst so small that it's only large enough to access one of these CH bonds at a time, we might be able to avoid oxidizing all of the other bonds. So the way we did that is we took gold nanoparticles, which are inert for any of these oxidizing reactions, and we took palladium, a metal that's very, very good at these CH bond oxidation reactions, and we wanted to add the palladium in single atoms or isolated atoms of palladium inside of gold. So in these catalysts, the gold is really just being used as a holder to stabilize these single atoms of palladium that we hope will only be able to access one of those CH bonds. So the way that we made these nanoparticles is a process called colloidal nanoparticle synthesis. And this is really what our lab here at Stanford specializes in, how to make these different types of nanoparticles. And this is, colloidal synthesis is a bottom-up synthesis technique. So I think you might talk about this a little bit later. But this is starting from kind of the very basic building blocks. If you want to think about it as an analogy to Legos, where each of these metal atoms is a single Lego, and we can start assembling them into various types of nanoparticles. Specifically with this palladium gold nanoparticle synthesis, we used what's called a seed-mediated process. So first we used colloidal synthesis to make gold nanoparticles. I think you guys talked a little bit about the cool properties of gold nanoparticles yesterday. We could then take those gold nanoparticles, add them to a different synthesis with controlled amounts of palladium, such that very, very small amounts of palladium could be added to the gold nanoparticles, such that we had these geometries that look something like this. And I don't need to get into the details here, but we were able to get amounts of palladium as low as 1 atomic percent. So 1 in every 100 atoms in these nanoparticles was palladium, and the other 99 were gold. So that gave us hope that we were getting those very, very small amounts of palladium into these gold nanoparticles. So just take a step back and to kind of talk about colloidal synthesis in general. For me at this point, there's a lot of analogies between making nanoparticles and baking cookies. So to start out, you need to find what your recipe would be. The scientific literature is filled with procedures to make just about every metal nanoparticle you can imagine. So you just need to find one that would work for the size and the metal that you want to make. You get all of your ingredients and you mix them together. Metal nanoparticles tend to have a few common ingredients. They're a high boiling point solvent. So something that will stay liquid and not boil at temperatures up to 300 degrees Celsius or higher. You need the metal salts that will be kind of those single Legos to make your nanoparticles. And you also need stabilizing molecules that will help these nanoparticles from kind of combining back together once you've made them. Once you've mixed all of the ingredients, then you need to heat them up. In the case of nanoparticle syntheses, this heat up process is done under nitrogen, both to reduce flammability hazards and to exclude oxygen from being incorporated into the nanoparticles. Likewise, it's important to remove all water since we are going to high temperatures. It would boil off violently at such high temperatures. And as I mentioned, these syntheses are conducted anywhere between 300 and 450 degrees Celsius. And this is kind of where one of the most important features of nanoparticle synthesis happens, and that's trying to separate these two phases of nanoparticle synthesis called nucleation and growth. If you're able to separate these two processes, you'll get very, very uniform nanoparticles. And as I mentioned, since nanoparticle size and shape are important for catalytic activity, it's important to get only one shape and one size of nanoparticles out of these synthesis processes so we can really understand what features are important for whatever catalytic reaction we're testing. So if we look at a synthesis flask at room temperature, with all of the ingredients mixed, they tend to be relatively clear liquids. And if we were to look at them very, very closely with TEM, we would see nothing. There's no nanoparticles formed at room temperature. Once we start heating the reaction up, though, once the nanoparticles start to form, you'll notice that the synthesis solution actually starts to change color rather dramatically, typically moving from these clear colors towards black. And if we were to look at TEM, once this nucleation process starts, we see these very, very small.
That was unexpected.
Angela, that happened to me. I was doing a Zoom meeting and I had 63 kids in, and my husband and daughter decided to make tortillas, and this fire alarm went, fire, and they couldn't turn it off. So yeah.
Okay, well, it's totally fine. Yep, a very exciting day. Never a dull moment on the internet. But that's totally fine. I actually wanted to, there was one thing that I wanted to talk about was when Cody showed the nanoparticles, I thought it's really cool. They're so tiny. So I just want to clarify. So it's like the nanoparticle is primarily gold, and then there's tiny atoms of platinum on top. And the actual nanoparticles, I think he put some estimates up, and they were like 3 nanometers in width and stuff like that. And so a 3 nanometer nanoparticle is so small that it's about like 20 atoms wide of gold, which I think is crazy. So if you calculated it out, they're really small, and so they're so tiny. Yeah. All right, so we'll wait until Cody is back and situated. I think that was a little bit of a challenge. But does anyone have any questions so far, since Cody's sort of in transit right now? on any of this stuff.
Is he going to share that PowerPoint with us?
Yeah, he'll share it with us. He shared me some of the slides, but I think he might have changed them since then. So I think he'll share them again. That shouldn't be a problem. Anyone else? Any other questions? Okay.
Yeah, Angela, I'm just speaking of particles, and I know we're filling the gaps until Cody comes back. Think about the ionizer that we use inside the house to clean our air. So when the ions attach to the particles, when we breathe them in, you think they are safe? Do you have any?
Yeah, they should be perfectly safe. An ion is just a charged particle. So, for example, actually, some of your face masks that you wear, one of the layers of the face mask is charged, and it's actually used to filter particles from coming in. So you want them to have kind of like a static cling, so the particles stick to your mask and things like that. And then I see had a question: is gold a vesicle or a vehicle for the platinum? And yeah. So the platinum is kind of riding on the gold nanoparticles. Yeah, and I see Cody is back. Cody, are you okay?
Yeah. How loud is the alarm in the background still?
You can't hear it at all.
Can't hear. Okay.
But Vicky, I just want to say you're not alone. Vicky was saying how she had a group of 60 students and her family tried to make tortillas and then started to burn down the house. So.
Yeah, I'm sure it's more common now with all the Zoom meetings. It's a first for me.
Yeah. All right. Well, if you're ready, we are ready. So take your time.
Yeah, are you good to just pick it back up?
Yeah, I think so.
Sounds good to me.
Okay.
Where were we?
Yeah, I think somewhere around there.
Yeah, I think we were right here, right?
Yep.
I think I was just trying to explain that separating this nucleation and growth steps are important for making uniform nanoparticles. So if you're able to separate that, in one step you'd have these nuclei, and then as you continue to increase the temperature, those nuclei would grow and form these very uniform nanoparticles. The difficulty being that if you have both nucleation and growth at the same time, you end up with nanoparticles with a lot of different sizes, where you have some very small nuclei that are just getting started, and other nanoparticles that have been growing for a lot longer time. So you'd end up with some small particles and large particles. Now, as I mentioned, that might make properties difficult to determine in the future. So once you've made the nanoparticles, you can move to prepare them. This was maybe a little bit of a stretch in the cookie analogy, but in this step that the nanoparticles are isolated, and then once we have the nanoparticles isolated, we can move forward to characterizing them and to put those nanoparticles onto their oxide supports. So I'm just going to show a few quick characterization processes here. I think you have somebody coming in to talk with you guys later about more advanced characterization. But one of the big techniques that we use in our group is electron microscopy. So this enables us to have images with magnification over hundreds of thousands of times better than the human eye. It works very similar to typical light microscopes, only instead of light, electrons are used. So here I'm showing you some TEM images of gold nanoparticles that we would use as carriers for those single palladium atoms. Another thing that we can actually do with gold is we can measure how those nanoparticles interact with light. So I think Angela showed you guys yesterday that the instances of gold nanoparticles and how their color can change with different size. We can actually use that to characterize these nanoparticles. So this technique that we're using here is called UV-vis spectroscopy. So we're basically measuring how much of each color of light is being absorbed. So here I'm showing you the scale of different colors and what wavelengths those correspond to. And the reason that gold nanoparticles look red like they do is actually because they absorb rather uniquely. So what's being shown here on this graph is the amount of absorbance. So basically, what fraction of that color of light is being taken up by those nanoparticles. And you'll notice that the absorbance of these gold nanoparticles is much higher in this purple to green area, leaving this red area open. And that's kind of why these particles appear on the red end of the spectrum. If we look at how those nanoparticles then compare as these small amounts of palladium are being absorbed, are being added, you see that actually the absorbance over in this area starts to go down. And we use this as an indicator to tell us that the palladium is actually being added to these gold nanoparticles, that the properties of the nanoparticles are being changed. And as a result, these nanoparticles no longer appear red. They appear closer to black. Some more advanced characterization techniques that we might be able to do is we can add something called energy dispersive X-ray spectroscopy onto TEM. So if you imagine the TEM images previously, when we add this technique onto TEM, we can start telling where different elements are. So in this upper left image, all of the green dots represent where palladium is. In this image, all of the red dots represent where gold is. And here the teal dots represent where titanium or the support for this catalyst are. So if you put them all together in one image, you see that the palladium and gold are actually located in the same nanoparticle. So this technique gives us a really cool way to visualize where these different elements are located within the catalyst. And maybe even more advanced than that, we were able to conduct some experiments out at the Stanford synchrotron radiation light source. So this is a Department of Energy facility that's operated in conjunction with Stanford. And it's a really great opportunity for us because there are only about 5 synchrotrons in the United States and less than 20 in the world. And we actually have one right in our backyard that we're able to run experiments with. I won't get into too many details of these experiments, but basically what we were able to do is determine how many palladium neighbors the average palladium atom has. So in the catalyst that we wanted all palladium atoms to have no palladium neighbors. And we were actually able to use this technique and determine that we did have those single atoms of palladium kind of located inside of these gold nanoparticles. So we were able to make the catalyst that we wanted. Once you've gone through all of the work to make your catalyst or to make your cookies, the final step is just to enjoy them. In catalysis, that would mean using them for chemical reactions. We run our reactions on relatively small scales. I'm showing you our catalytic reactors here. They're these glass U-tubes, where this small amount of dark powder is the catalyst powder that we've been making in these previous steps. We used maybe up to 100 milligrams of catalyst powder in each test. As I mentioned at the top, this was the holy grail of catalysis, and it turned out it was actually a very difficult reaction to get to work. We were really only able to make, again, complete combustion catalysts. We weren't really successful at converting methane into methanol. But actually, these catalysts did turn out to be good at less demanding selective oxidation reactions. So this is just an instance of showing the amount of activity that these catalysts had as a function of palladium. And as we expected, actually, or as we hypothesized, the smallest amounts of palladium were actually the best for these catalytic reactions. But with that, I'd like to thank you guys for your attention and for bearing with me through the fire alarm, and I'd be happy to answer any questions that you might have.
Thank you. Can everybody give him a thumbs up or a something for doing that? Yeah, thank you.
May I ask a question if I can?
Yes, of course.
Cody, now what necessitates converting methane to methanol when both are abundantly available?
Yeah, the big difference is the phase or gases versus liquids. So the reason methane can't be recovered in these remote locations is because it's a gas. So if it could be converted into a liquid, it could then be recovered rather than being flared and wasted. So that's kind of why people want to transform methane into a liquid product.
And my second question is, when you add oxygen to methane, like I think I'm assuming it's a fusion reaction, what method do you use? Does it require like high pressure, heat, or electrical current to add that oxygen atom?
Mm-hmm. So we work primarily with thermocatalysis reactions, so where we're using heat to drive the reaction. But there are other people in the group that use electrocatalysis, so use electrical currents to achieve these reactions, as well as photocatalysis, where people are using light to drive these reactions. So these catalysts can be used in a variety of different ways, but I focus on thermocatalysis.
Oh. And one more thing, you mentioned that if we add oxygen to all those 4 hydrogen atoms, in the molecule, what product do you get if you add the oxygen to that?
Right. If you add the maximum amount of oxygen to that methane molecule,
hydrogen atom.
Yeah, you get carbon dioxide and water.
Oh, okay. Okay, great.
Great, thank you, Cody. Does anyone have any other questions? Again, if you're a little shy, feel free to use the chat box as well. I'm monitoring it. Everyone is saying thank you, by the way, Cody. And yeah. All right. So if anyone doesn't have any more questions, I think we'll thank Cody for his time and his fire alarm excitement.